HVAC source equipment for cooling Part 1. Welcome to this comprehensive course on HVAC source equipment for cooling Part 1. In this course, we'll explore the fundamental components, systems, and processes that power efficient heating, ventilation, air conditioning, and refrigeration solutions. You'll gain in-depth knowledge about refrigeration cycles, types of refrigeration systems, compressors, air and water-based cooling, and much more. Let's break down the main parts of HVAC systems. These systems rely on 4 key types of components to keep our indoor spaces comfortable and efficient. Source components, think of these as the heart of the system. They're the ones responsible for creating the heating or cooling effect. Examples include boilers, heat pumps, and air conditioners. Distribution components, once the heating or cooling is created, it needs to travel to where it's needed. That's where distribution components come in, like ductwork and piping, moving air or liquid through the system. Delivery components, these are the final step. Delivery components are what actually bring the heated or cooled air or liquid into your living or working spaces. Think vents, diffusers, or radiators that ensure you feel that comfortable temperature. Control components, and finally, we have control components. These are like the brains of the system, making sure everything operates safely, efficiently, and maintains just the right level of comfort. Examples include thermostats, sensors, and advanced control systems. These 4 types of components: source, distribution, delivery, and control work hand in hand to keep our homes, offices, and factories at just the right temperature, saving energy and ensuring comfort every day. Let's uncover the workings of refrigeration systems, designed to remove heat from a refrigerated space and transfer it to the atmosphere. It operates based on the principles of thermodynamics, using a refrigerant fluid to absorb heat from the space and release it outside. In diagrams, the color red typically represents the heat being removed from the refrigerated space, while blue indicates the cooled air or environment within the space. This process helps maintain the desired temperature in various applications, such as food storage, air conditioning, and industrial cooling systems. Let's understand the refrigeration cycle. The vapor compression refrigeration cycle is a common method for cooling spaces. It involves 4 main components. Compressor compresses low-pressure refrigerant vapor, raising its temperature and pressure. Condenser releases heat to the surroundings and condenses the vapor into a high-pressure liquid. Expansion valve reduces the pressure of the liquid refrigerant, causing it to partially vaporize and become very cold. Evaporator absorbs heat from the environment, evaporating into a low-pressure vapor, completing the cycle. Energy flows. W. Work input to the compressor. Q_H. Heat rejected from the condenser to the environment. Q_L. Heat absorbed by the evaporator from the surroundings. Let's look at the 5 main types of refrigeration systems, each using unique principles and technologies to provide cooling. Vapor compression, the most common system, where a refrigerant is compressed, condensed, and expanded in a cycle to remove heat. Air cycle, uses air as the refrigerant, typically in aviation applications. Absorption, relies on a heat source to drive the refrigerant cycle, using absorbents like lithium bromide or ammonia. Thermoelectric, uses the Peltier effect to create temperature differences for cooling. Evaporative cooling, involves the evaporation of water to cool air, commonly used in arid climates. Let's explore the vapor compression refrigeration system, which cools a specific space by transferring heat from a low-temperature area to a high-temperature area. Components and process. Evaporator, located in the area to be cooled, absorbs heat and evaporates the refrigerant into a low-pressure vapor. Compressor, increases the pressure of the low-pressure vapor, raising its temperature. Condenser, releases heat to the external environment, condensing the vapor into a high-pressure liquid. Expansion valve, reduces the pressure of the high-pressure liquid, causing it to expand and become a low-pressure mixture. The cycle repeats, efficiently transferring heat and cooling the space. Let's examine the two-stage refrigeration cycle, which provides cooling by transferring heat from a low-temperature environment to a high-temperature one. The two-stage cycle consists of components such as a condenser, flash chamber, evaporator, water intercooler, compressor I, and compressor II, with heat input, Q, as the input and heat rejection, Q, and work output, W, as the outputs. Process. The cycle uses two compressors and an intercooler to achieve a two-stage compression cycle. The refrigerant is compressed by the first compressor and then passed through a water intercooler before being compressed again by the second compressor. The refrigerant then condenses in the condenser, rejecting heat to the environment. The refrigerant then enters the flash chamber, where a portion of it vaporizes and is expanded in the evaporator, absorbing heat from the surroundings. The remaining refrigerant liquid is then sent back to the evaporator to complete the cycle. Let's explore the cascade refrigeration system, consisting of two interconnected refrigeration cycles, a high-pressure cycle and a low-pressure cycle. The high-pressure cycle extracts heat from the low-pressure cycle using a heat exchanger, allowing the low-pressure cycle's evaporator to operate at a lower temperature. This configuration enhances the refrigeration capacity of the low-pressure cycle while reducing the overall work input required for a given refrigeration output, making it efficient for applications requiring very low temperatures. Let's explore the cascade refrigeration cycle. The cascade refrigeration cycle utilizes two separate refrigeration cycles that are linked by a heat exchanger. The cycle consists of two condensers, two evaporators, two compressors, and a heat exchanger. The high-pressure cycle operates at a higher temperature than the low-pressure cycle. The high-pressure cycle condenses the refrigerant at a higher temperature, while the low-pressure cycle evaporates the refrigerant at a lower temperature. The heat exchanger allows heat to be transferred from the high-pressure cycle to the low-pressure cycle. This allows the low-pressure cycle to operate at a lower temperature, which can be used to cool a space or product. The cascade refrigeration cycle is a more efficient way to cool a space or product than a single-cycle system. This is because the high-pressure cycle can operate at a higher temperature, which reduces the amount of energy required to cool the space or product. The system is designed to minimize work needed while maximizing refrigeration. Refrigerant supply types refer to how the refrigerant is distributed and used in refrigeration systems. The main types are direct expansion, DX, systems. Refrigerant flows directly through the evaporator coil, absorbing heat and evaporating. Flooded systems, the evaporator is flooded with refrigerant, maintaining a constant level for efficient cooling. Recirculation systems, a portion of the evaporated refrigerant is returned for reuse, ensuring continuous heat absorption. Direct expansion, DX, refrigeration system. The DX refrigeration system operates as follows. Evaporator, the refrigerant enters as a low-pressure liquid, absorbs heat, and evaporates into a vapor. Compressor, the vapor is compressed to a high-pressure gas, increasing its energy level. Condenser, the high-pressure vapor releases heat and condenses back into a liquid. Expansion valve, the liquid refrigerant's pressure is reduced, causing it to partially vaporize. Cycle repeats, the low-pressure mixture returns to the evaporator. The flooded refrigeration system operates as follows. Key components. Float chamber, holds liquid refrigerant. Float control valve, regulates refrigerant flow into the evaporator. Evaporator, absorbs heat, causing refrigerant to evaporate. Accumulator, removes liquid refrigerant from vapor before it enters the compressor. Compressor, compresses the refrigerant vapor. Condenser, cools and condenses the vapor back into a liquid. Process, liquid refrigerant is stored, controlled, and circulated to absorb heat, ensuring efficient cooling. The recirculation system, specifically a cooling tower system, works as follows. Warm water enters from a heat source. Heat exchanger transfers heat to the air inside the cooling tower. Cooling tower, warm water is sprayed and cooled by air, which absorbs heat through evaporation. Cold water, cooled water is collected and pumped back to the heat source. Make-up water, added to maintain water levels due to evaporation losses. Air or water-based cooling. Air or water-based cooling systems utilize vapor compression refrigeration to transfer heat and provide cooling. Air-based cooling, in this system, air is blown over the evaporator, where it absorbs heat from the refrigerant, causing the refrigerant to evaporate and cool the air. The warmed air is then expelled, while the refrigerant is compressed and passed through the condenser, where it releases heat back to the environment. This method is commonly used in air conditioners and cooling units. Water-based cooling, alternatively, water can serve as an intermediate cooling medium. In this setup, the refrigerant absorbs heat from the water in the evaporator, cooling the water that is then circulated through spaces needing cooling. The refrigerant is again compressed and passed through the condenser, where it releases heat. This method is often more efficient, especially in larger systems, as water has a higher heat capacity than air, allowing for better heat transfer and more effective cooling. Overall, both air and water-based cooling systems leverage vapor compression to effectively manage heat and provide temperature control in various applications. Let's compare an air-cooled chiller with a traditional chiller. An air-cooled chiller operates by compressing, cooling, and expanding refrigerant to absorb heat. Here, water is used to cool the condenser, and warm water is sent to a cooling tower for further cooling. Now, a traditional chiller follows a similar process but might differ slightly in design and application, depending on the specific requirements. For instance, traditional chillers can sometimes include water-cooled systems that rely on a cooling tower or other methods to enhance efficiency. Understanding these distinctions helps in selecting the right system for your cooling needs. Variations of evaporators and condensers. DX systems, refrigerant evaporates inside the coil, commonly used in smaller applications. Chilled water systems, refrigerant cools water through a heat exchanger, used in larger applications for efficient cooling. Air-cooled condensers, release heat directly to air, suitable for smaller systems. Water-cooled condensers, use water to absorb heat, more efficient for large systems. Direct expansion, DX, air conditioning system. Components. DX evaporator, absorbs heat from indoor air. Compressor, compresses the refrigerant, raising its pressure and temperature. Air-cooled condenser, releases heat to the outside air. Expansion valve, reduces refrigerant pressure, causing it to evaporate and absorb heat. Filter, removes dust and particles from outdoor air. Mixing box, controls temperature and humidity by mixing outdoor and indoor air. Variable speed drive fan, circulates air through the system, enhancing airflow and energy efficiency. Cooling cycle. The refrigerant enters the evaporator as a low-pressure, low-temperature liquid. It absorbs heat from the indoor air, evaporating into a gas. The compressor compresses the gas, raising its pressure and temperature. The high-pressure refrigerant enters the condenser, where it releases heat and condenses back into a liquid. The liquid refrigerant passes through the expansion valve, where its pressure drops, allowing it to evaporate and absorb heat again. Air circulation. Outdoor air is filtered and mixed with indoor air in the mixing box. The mixed air is cooled by the evaporator and circulated throughout the air-conditioned space by the variable speed drive fan. Chilled water system. The chilled water system uses chilled water to cool buildings. Components. Cooling tower, removes heat from the system by cooling warm water. Electric chiller, cools water below the temperature of the cooling tower. Air handling units, Ahus distribute chilled water to cool the building. Compressor, compresses refrigerant gas, raising its temperature and pressure. Condenser, cools the hot refrigerant gas, transferring heat to the cooling tower water. Evaporator, cools and vaporizes the refrigerant, absorbing heat from the chilled water. Valve, controls the flow of chilled water to the Ahus. Fan, circulates air through the cooling tower and Ahus. The system operates in a closed loop, with water being cooled and circulated to maintain comfortable indoor temperatures. Cooling tower. A cooling tower removes excess heat from water-cooled systems through evaporative cooling. Process. Warm water circulates through fill media, where it is exposed to air. A portion of the water evaporates, lowering the temperature of the remaining water. The cooled water is recirculated back into the system. Key components. Fan, moves air through the tower. Fill media, increases surface area for heat exchange. Drift eliminators, prevent water droplets from escaping with the air. Cold water basin, collects cooled water for recirculation. Cooling towers are essential for maintaining energy efficiency and system stability in HVAC applications. Let's talk about the reciprocating compressor, a real powerhouse in many cooling systems. It works by compressing refrigerant gas to increase its pressure and temperature, getting it ready for the next stage. Here's the process. Inside the compressor, a piston moves up and down in a cylinder. When the piston moves down, it pulls in refrigerant gas. Then, as it moves up, it compresses the gas and pushes it out at high pressure into the condenser. What makes it great? Well, it's reliable, efficient, and versatile, perfect for small to medium-sized systems. That's why you'll find it in so many cooling applications. Next up, let's look at the rotary compressor, a smooth operator in the world of refrigeration and air conditioning. This compressor uses a rotating mechanism to compress refrigerant gas. The key components are a cylinder, a rotor, and blades that rotate inside the cylinder to compress the gas efficiently. Why choose a rotary compressor? It's quieter and more compact than its reciprocating counterpart, making it ideal for medium to large air conditioning and refrigeration systems. If space and noise are concerns, the rotary compressor is a top pick. Now let's talk about the scroll compressor, an innovative solution in the HVAC world. This type of compressor uses two spiral-shaped scrolls to compress refrigerant gas. Here's how it works. One scroll stays stationary while the other moves in an orbiting motion, trapping and compressing the refrigerant smoothly and efficiently. What makes scroll compressors stand out? They're known for being quiet, efficient, and incredibly reliable. Whether it's for residential or commercial cooling systems, these compressors deliver exceptional performance with minimal noise and maintenance. Let's dive into the screw compressor, an industrial powerhouse in the world of HVAC systems. This compressor operates with two interlocking helical rotors that work together to compress refrigerant gas. As the rotors turn, they trap the gas and gradually compress it, creating a smooth and efficient process. Why choose a screw compressor? It's known for its high efficiency, durability, and ability to handle demanding applications. Perfect for industrial and commercial HVAC systems, it offers continuous, reliable operation with minimal vibration, making it a trusted choice for large-scale cooling needs. Next up, let's talk about the centrifugal compressor, a key player in large-scale cooling systems. This compressor uses a rotating impeller to do its magic. Here's how it works. Refrigerant gas is drawn into the center of the impeller, then accelerated outward at high speed. This creates the high-pressure gas needed for the condenser to operate effectively. So, why is it so popular? Centrifugal compressors are known for their high efficiency and ability to handle large volumes of refrigerant. That's why you'll often find them in massive commercial and industrial HVAC systems, where reliable and continuous performance is an absolute must. Thank you for joining us on this journey through HVAC systems and refrigeration technology. We hope this course has provided you with valuable insights, practical knowledge, and a deeper understanding of the key concepts and processes that drive efficient HVAC and refrigeration systems. The upcoming topic is HVAC source equipment for cooling Part 2.